When we look at a small airplane, a passenger jet, and a fighter aircraft, their wings can look completely different. Some wings are almost straight, some sweep backwards, some are shaped like triangles, some even have small vertical pieces at the tips. These shapes are not chosen only for appearance. Every part of the wing has a purpose. Air travel is common, but most passengers do not know why wings are curved, why they're moving during takeoff and landing, or why different airplanes use different designs. I've been interested in aircraft and model airplanes since high school, so I chose to research this topic using one aerodynamic textbook and 4 academic journal articles. Today, I will explain 3 things. First, I will explain how the basic shapes of wing creates lift. Second, I will explain why wings changes shapes during different part of flight. Third, I will explain why different aircraft use different wing designs. First, how does a wing create lift? According to John Anderson's textbook, Fundamental of Aerodynamics, the shape of an airfoil and the airflow around it is the center of producing lift. An airfoil is simply a shape of a wing. We looked at it from the side. It usually has a rounded front, a thin rear, and some curve across the surface. Anderson's book covers airfoil characteristics, real airflow over airfoils, and the lift generated by wings. As the airplane moves forward, air flows around the wing. The wing changes the movement of that air and also creates a difference in pressure around the wing. Together, these effects produce an upward aerodynamic force, and that's called lift. And lift helps the support of the weight of an airplane. The angle of the wing also matters. When a wing changes the angle, becomes a little larger, the wing can usually create more lift. However, if the angle becomes too large, the airflow may separate from the wing instead of flowing smoothly. When that happens, lift drops and the wings can stall. A 2008 article by Nick Tula and his co-authors explained that wings also create swirling air near its tips. This wingtip airflow creates a type of resistance called inducing drag. In simple terms, inducing drag is some of the energy lost while the wing is producing lift. This is why wing design must think about both lift and drag at the same time. A wing must create lift, but one fixed shape cannot work equally during takeoff, cruising, and landing. This leads to my second point. Wings sometimes change shape. During takeoff and landing, an airplane travels more slowly than it does during cruise. To create enough lift at these lower speeds, many airplanes lower flaps of the rail of the wings. Flaps makes the wings more curved and help it produce more lift. Researchers also studying wings that can change shape more smoothly. In a 2025 study, Cottomott and his colleagues compared continuously changing wing shapes with a traditional hanging flap. Under the condition they tested, the smooth changing shape produced more lift with the same amount of movement at the back of the wing. However, it could also create more drag. This shows an important idea of engineering. Improving one part of a performance can sometimes create a new problem somewhere else. Small aircraft can face additional challenges. A 2024 study by Mei-Ling Yue and her colleagues examined airflow over small UAV wings. They found that airflow separation and background turbulence can strongly affect the wing performance. Under some test conditions, turbulence reduces separation and delays stall. However, this study focused on small UAVs, that's low Reynolds numbers. This simply means that aircraft and airflow conditions were very different from those of the large passenger airplane. We should not assume that the result applies in exactly the same way to every aircraft. My third point is that different missions require different wing designs. Nikolai and his co-authors describe several major wing shapes, including rectangular, elliptical, sweep, and delta wings. These shapes have different advantages. For example, sweep wings are usually useful for the fast flight below the speed of sound, which is why they're common on passenger jets. Delta wings are usually often used for supersonic aircraft because they work really well at very high speed. Some aircraft also have winglets at the end of their wings. Winglets help reduce the effect of the swirling air near the tips. By reducing those effects, winglets can reduce the induced drag. At a much smaller scale, the wings can work at a very different way. In 2001 study, Zhou and Hadamni examined an airfoil moving in rapid insect-like hovering motion. They found that quick rotation and a strong vertical could briefly create very high lift. Their study does not describe the normal passenger airplane. It has designed to help explain the flight of horizontal insects. However, it shows that wing design and the wing motion can change greatly when the size of the mission are different. To conclude, I discussed three main points. First, the basic shape and angle of the sweep wing help create lift. Second, the wings can change shape during takeoff and landing to work better at lower speeds. Third, different aircraft use different wing designs because they have different speed and mission requirements. Airplane wings are shaped to generate lift, work well in different parts of flight, and meet the need of each aircraft. The next time you see an airplane, look closely at its wings, the curve, moving parts, and sweep angles, and the wingtips are not decorative details. They are a visible answer to the challenge of flight.